We have already presented Newton's three laws of motion, which are the fundamental laws of mechanics. However, another principle was established by Leonardo and Stevin, which is also of crucial importance in mechanics. In the previous examples, we studied forces which were exerted on a given body by another body or a group of bodies. A special case of them was a body suspended from a spring or was at rest on a table, where only two forces acted on the body. We saw that the static measurement of force is based on the fact that a point-like body at rest will remain at rest, if two forces with the same magnitude and the opposite direction act on it. Now we present the following experiment studying such a static case, which helps us to demonstrate Leonardo and Stevin's principle. We suspend three bodies with the weights F1, F2 and F3, where the strings used for the suspension are tied at the ends with a knot in the point P. The strings attached to the bodies with the weights F1 and F2 pass over two fixed pulleys. For the given weights F1, F2 and F3, we can find an angle between the directions of the strings passing over the pulleys such that the system is at rest, that is, the forces acting in the system are balanced. Since the strings can transmit the forces exerted by the suspended bodies to the knot at the point P, the forces F1, F2 and F3 act at the point P. By virtue of the first law, the body of the weight F3 can only remain at rest if the net force acting on it is zero. That is, the net effect of the forces F1 and F2 at the point P is equivalent to the opposite of the force F3. Therefore, the criterion of the force balance in the system is that the force minus F3 acting in the point P can be replaced with the forces F1 and F2. The force minus F3 can be constructed by applying the parallelogram law for the vectors representing the forces F1 and F2. As a result, the effect of the force minus F3 is equivalent with the effects of the forces F1 and F2, provided the force F3 is the vector sum of them. This can be achieved by adjusting the angle between the strings in the experiment setup. Then we can conclude that two forces acting at one point can be replaced an equivalent force, which is the resultant of those forces. Since the parallelogram law allows us to add and decompose forces acting in a given point as vectors, force can be regarded as a vector. This conclusion was reached by Leonardo and Stevin when they studied problems related to statics. But everyday experience shows that this principle holds under general conditions and can be applied throughout physics. Since Leonardo and Stevin's principle is valid in general, it is also known as the fourth law of motion. In its general form, this law states that if the forces F1, F2, Fn simultaneously act on a point-like body, then the net effect of these forces is equivalent to the vector sum of these forces, that is, the net force F is equal to the sum of Fi, where the index I runs form 1 to n. Therefore, the fundamental equation of dynamics applied to a point-like body with the mass m is the following: the mass m of the body times its acceleration a is equal to the force F, which is the vector sum of all the forces acting on the body. The fourth law of motion can be expressed in another form, which is known as the principle of the physical independence of forces or the superposition of forces. We present this form of the fourth law with a simple example, where we study the simultaneous and the separate action of two forces on a body. If either the force F1 or F2 acts on the point-like body of the mass m, then the second law of motion states that the acceleration of the body is either a1, which is equal to F1 divided by m, or a2, which is equal to F2 divided by m. If the two forces act on the body simultaneously, then the net force exerted on the body is F1 plus F2, and the acceleration a of the body is equal to F1 plus F2 divided by m. The right-hand side of the equation can be written as F1 divided by m, plus F2 divided by m, which is equal to a1 plus a2. In fact, this expression is not the sum of the individual equations for the accelerations a1 and a2, but the consequence of the fourth law. The addition of the two vector equations is based on the assumption that the force F1 produces the acceleration a1, that is, the force has still the same effect on the body, even if the force F2 acts on the body, and vice versa. The effect of the force F2 is independent on the effect of the force F1 as well. If the effect of the force F1 changed the original force F2 acting on the same body to F2', then the acceleration of the body were F1 plus F2' divided by m, which is not equal to the original acceleration. The fourth law, as a principle established by experience, claims that the forces acting simultaneously on the point mass have no effect on each other, and the net effect of these forces on the body is the superposition of their individual effects. Therefore, this law is also called the principle of physical independence of forces or the principle of the superposition of forces. The fundamental equation expressing the principle of the superposition of forces gives the answer to the basic question of statics: which is related to the criterion of the equilibrium of a mechanical system. This equation tells us that the acceleration a of a body is proportional to the net force acting on it. We examine the question in statics, where the body is at rest and there is no motion, that its acceleration vanishes. In fact, we are interested in the equilibrium of the body, which can be defined as follows. A body or a group of bodies under the influence of external forces is in equilibrium, if it is at rest at a given time, and it will remain at rest. For example, a point mass performing simple harmonic motion is not in equilibrium in the turning points of the oscillation, since its velocity is not zero there. The question is under what condition a point mass at rest will remain at rest, while forces act on it. By virtue of the fundamental equation, the necessary condition of the equilibrium of a point-like body is that both its velocity v and acceleration a vanish, that is, the net force acting on the body is zero. Since the net force is given by the vector sum of all the forces acting on the body, that sum must vanish. Conversely, if the vector sum of the forces, that is the net force acting on the body, vanishes, then the acceleration of the body is zero. However, this is not a sufficient condition as to ensure the state of rest, since the vanishing acceleration of the body can allow the body to have a constant velocity, which holds for uniform rectilinear motion. For a necessary and sufficient condition, we also suppose that the point mass is at rest in a given instant of time, that is, its velocity is zero at that time. If the net force acting on the body is also zero, then its vanishing acceleration already guarantees that the body will remain at rest, that is, the body is in equilibrium. Then the necessary and sufficient condition of equilibrium of a point-like body is that its velocity is zero at a given time, and the forces acting on the body are balanced.